Hello, Zamfam. This is Mr. Kennedy, your Models of Physics teacher. Want to wish you a happy Monday. Hope your weekend was well. Mine was a little bit bizarre, celebrating Easter in a different manner. But we made the best of it. I hope you guys did too, and everyone's well. This week we'll probably do a Google Meet just so I can see all your faces, say hello, check in with you. We are going to finish up this unit on central net force. I realize this last worksheet is very difficult. That's why I am going to walk you through the first problem. And then later in the week I'll see if you guys are confused about the rest of them and can answer any questions. Okay, ready to get started? Let's do this. Alright, so again, I have my handy dandy American Girl doll stand. La la, let's not make it fall over. We are gonna go over, can we see that? This problem right there, number 1, where we have a satellite orbiting the moon. So this is pretty cool stuff, because yes, there are some equations, yes, there are some math, but it's all stuff that you can do. Thanks to good old Newton's universal law of gravity. Hey, Jolie, want to come say hello? Come on, say hello to my Stefania. I know you know her.
Estefania.
Estefania.
You got it.
All right, do you want to help teach this class,
No.
Jolie? You've done this stuff already.
No, I haven't.
You're probably an expert.
What have I done?
All right. So let's take a look at the first part of this. Got to put her. Wonder Woman says hello. All right, great part of this quarantine because I've watched a lot of Marvel movies. Haven't watched any before this, so on track to watch all 430 of them. I'll let you know how I'm doing on that. All right, let's do this. Zoom in, zoom out, get it just right. All right, so this first bit, what does one ask? Just for the weight of this satellite. And to get weight on any planet or anywhere in space, we're just going to multiply the gravitational field number. On our planet, it's 10 or 9.8, 9.81, if we want to be a little more precise, at sea level. And we multiply it by the mass. But we are not on our planet, we're on the moon, which has a lot less mass. So this actually G number is going to be a lot less as well. Everyone can probably dunk a basketball on the moon because the pull of gravity that the moon pulls on us is significantly less, only 1.6. So they get the weight of the satellite, and they say it's like right on the surface, is going to be 1,500 kilograms, the mass times the G value for the moon, which is 1.6. So we get with sig figs, yes, we love our sig figs, 2,400 newtons. Okay, easy peasy, right? All right, let's take a look at lower. Can I get lower? Oh, I get lower. Oh, pull it back. There you go. All right. What do they ask for now? They ask for the radius of the orbit. All right, so this is where it gets a little bit tricky. Now, if the satellite is just resting on the surface of the moon, we would take just this R value, and that's the radius of the planet, because I always go from the center of mass, the center of the planet, to the object that it's interacting with when we talk about gravitational forces. But if we want this radius of the orbit, we have to take both the radius of the planet from the center of the moon to the surface, and then it's gonna be floating up above the surface a little bit, zooming around like our communication satellites do, above the surface of the planet. So we have to add those two parts. So we know when we're given this problem that the radius of the moon is 1.74 times 10 to the 6 meters. And then there's the tricky parts. They actually say that this satellite is orbiting 100 kilometers above the surface of the moon. So this is similar, like some satellites that we launch are about this high up. Pretty significant distance. 100 kilometers, I don't know, here to Kankakee, maybe Champaign, Illinois. So significant distance above the surface. So we have to add those two numbers. Now, if we want to get really fancy and cool and efficient with our adding, we can actually change this into a value that has the same magnitude of tens as this number, because this number is pretty big. It's times 10 to the 6th. You can just add this in a calculator. Type this in, 1.74 times 10 to the 6th plus 100,000. Bam, you'll get the answer. They might even give it to you in sig fig notation if you want, or set it up in your calculator. You can figure that out yourself. Or you can say, hey, 100,000 meters is the same thing as 0.1 times 10 to the 6 meters. I just move the decimal place over 6 times, making this number smaller, so I make this number bigger. That way, then it's really easy to add. If they're the same bases, you just add the numbers. All right, but we're not going to get too into that. That's what your math class is for. 1.74 plus 0.1 is just 1.84. And then we tack on that times 10 to the 6th. All right, so that's the overall radius that we're going to have to use in a sec. All right, I'll shut up, let you look it up. Okay, feel free to pause me at any moment. And comments down below. You're supposed to like and do something else. I don't know. I've also been watching some ZamFam videos to get some tips and pointers on, how to go viral and become a YouTube millionaire. All right, now it asks for the centripetal force. So how will we get centripetal force? What is allowing this sucker to orbit the moon? It's actually getting a free ride. Satellites. What the heck is on my... No, I'm not bleeding. It's just color. These satellites get a free ride. All right? No, someone said there's no such thing as a free lunch, but satellites sort of get a free lunch. They're just falling around the moon. Satellites do not have, gasoline or rocket fuel or any sort of thing that they would have to burn to go around this thing. They're getting on the free ride of gravity. Gravity pulls them around this planet. The force of gravity that is provided by the moon. All right, the satellite also pulls the moon, but that's just not important right now because the moon's really big. All right, so if we can figure out the force of gravity between these two objects, we could figure out the centripetal force. So we know that force of gravity, universal force of gravity, is just big G times the two masses divided by R squared. Now, here comes the math. Yes, and if you want the A++ in this corner, you'll have to do some of these, not a lot. I'm not going to over math this stuff up. But this is why I gave you the sig fig little review here. What you only need to do, this looks super complicated, but shortcut here. You're just going to deal with the numbers and the tens with the tens. So what I mean? Well, let's first square stuff. Good old PEMDAS, we always square stuff first. We're going to square 1.84 times 10 to the 6. And the way we do that is we just square the 1.84. We get 3.39 with 3 sig figs. And we square the 10 to the 6. Now, a power to a power you should have learned in your math class. If not, learn it now. Power to a power, we just multiply those two numbers. So that becomes 10 to the 12th. So we're just squaring that bottom part right there. If you want to do it in a calculator, you can. You'll end up with this. It'll be nice and shorter and easier if we just learn how to do it almost in our heads. All right, you're going to have to do 1.84 in a calculator, but if we get it all to where now we just deal with numbers and some times 10 to a certain power, now we can say, hey, give me that green number times this blue number divided by this red number, and what do I get? I get, what, 21,761? Sorry, reading this backwards, but I think I did a good job on that. Okay, that's just the numbers. Blue, or green times blue divided by red gives us that value, and we write that value down. Now we take a look at these exponents. This is 10 to the 22nd. Ooh, that's a big, big number. All right, that's the mass of the moon. Earth is even bigger. Sun's even bigger. And we have a small sun, but that's another day. All right, now we have to divide. When we divide same base exponents, ooh, you remember that. You just subtract those two numbers. All right, so we got, did I do this right? No, did I do this right? What the heck did I do here? 22. And then we got divided by 12. And we get a, that should be times 10 to the 10th, shouldn't it? Hold on a second. Oh, what did I do there? I forgot this good old one. The big G. Yeah. You, hold the phone. Here we got to multiply 6.67 times 7.36 times 1500 divided by 3.39. We don't need wise remarks from the peanut gallery. Go back to your TikToks in your room. All right, so I forgot this one. Whew, I was worried there. I was going to have to start this video over. 6.67 times 7.36 times 1,500. Then press enter, then divide by 3.39. Then you get 21,721. Now we get the exponents. Like base exponents that are being multiplied, we just add those numbers. Negative 11 plus a positive 22 gives us a positive 11. Positive 11, and then we have a 12. When we divide them, we subtract. So this is sort of math review, algebra review. And we get a 10 to the negative 1. So here we have it. It's sort of scientific notation, but not really, because this has to be a number between 1 and less than 10. But we still got that base negative 1. What does that mean? We're just going to divide this number by 1 or move the decimal place over. There we go. So this number is actually, about 2,000. But with sig figs, we'd round that up, it'd be 2,200 newtons. Or if we want to write in scientific notations, which is fantastic, we could say 2.2 times 10 to the third. This absolutely always tells us how many sig figs we have. That's the beauty of scientific notation. That's why you all passed that wonderful test. Okay, keep on moving. Pause it if you need it. All right. Bye-bye. All right. Ooh, we got lots of colorful little equations up here now. All right, we always got our good old F equals ma, our green equation. Then we got centripetal force. If you want something to move in a circle, this is the law. You gotta have this. And how much do you gotta have? You gotta have its mass times its velocity squared divided by the radius of the circle that's going to go around it. And then, thanks to good old Newton's sort of fourth law, the universal gravity equation, we could take the big G times the two masses divided by the r squared, and we know how much force of gravity is being pulled equal and opposite between the two objects. So, I think that's for velocity. How fast are these satellites going to be going? And this is how fast, we can and will figure out how fast the astronauts who are floating above us in the International Space Station, who sort of zoom around us, 6-7 times a day, how fast they're going. If we want to know how fast this moon satellite's going, I'm not sure why we haven't sent a satellite to the moon. Probably should. Can someone talk to someone? Get a satellite going around the moon. Sort of be fun. So what do we know? We know the force of gravity between these two objects. The moon pulls on the satellite with 2,200 newtons of force, actually, and the satellite pulls on the moon with 2,200 newtons of force. Thing is, the moon doesn't really care. Not much of a pull. And we know that's the centripetal force to make this thing go round. Ooh, look at that. We can say, hey, we know the mass. We know the radius. Let's solve for the velocity. Ooh. So we say, well, we need to divide both sides by the mass to get it on the other side, multiply both sides by the radius to get it on the other side. When we do that calculation, what do we get? We get 2.7 times 10 to the 6. Okay, that's a pretty darn big number. If you're good, you can actually write 2.7 E6 if you want to be a little bit lazy on your calculator. And then we got to take the square root of that number. You can also just write out this number with all its digits and then take the square root on the calculator. You get V all by itself. We get 1,643.17, but that is a lie. We don't have that precise of inputs. We can probably only say that it's going about 1,600 meters per second, 2 sig figs. If we wanted to write in scientific notation, we could. 1.6 times 10 to the third meters per second. All right, that's cool. We can figure out how fast satellites are going. Awesome. All right, that's deep. All right. Ooh, give me a long one. All right, I'm going to keep this under 20 minutes. All right, how long is it going to take? Ooh, this is something called a period. Another cool physics word we're going to learn. Period just means how long it takes to go with either one cycle, one orbit, one back and forth. So we use period for a lot of things. We're going to use it for orbit. So how long does it take go from there to back to its original spot? You know, like a sort of period of our orbit around the sun, we'd call 1 year. All right, so what's going on here? It's going to go around this circle. Ooh, can we figure out that distance? That is just the circumference of that circle. To get circumference, you just do 2 pi r. Oh, so if we get that distance, and we already know its velocity, distance is equal to velocity times time, right? Or time is just distance divided by velocity. So 2 pi times that r value, you know, both the radius of the moon and that 100 kilometers, that big r value, we got there. And we multiply by 2 pi. And to get that overall distance, this orange bit, and we divide it by 1,600. Lo and behold, what do we get? We get about 7,300 seconds, which with sig figs is 2.0 hours. Wow, that's fast. That'd be a cool little ride to go around the moon in 2 hours. All right. Oh, and last one. I snuck it in here. Gonna make this under 20 minutes, hopefully. Acceleration. Is it accelerating? You don't have to think too hard. Anytime something is turning, it's accelerating. Objects at rest, stay at rest. Objects in motion, stay in motion. In a straight line. In a straight line. If it's not in a straight line, it must be being pulled in some direction, probably towards the center of that little imaginary circle that we drew out. So it is accelerating. How much is accelerating? Ooh, F equals ma. A equals F over m. How much force is it pulling? We already figured that out. They're pulling each other with 2,200 newtons of force. And what's the object's mass? 1,500. So that rate of acceleration is 1.47. Interesting. It's a little bit less than on the surface, but that is the case. That's only on the surface. If we went up 100 kilometers, decided to... Ooh, I saw Captain Marvel, and she's able to fly up probably 100 kilometers when she's smashing Thanos or Rogan or whoever the heck it was. If we flew up 100 kilometers, there would be less of a force of gravity on us. That G value declines as your radius increases. All right, that's it for now. Hope you guys are all doing well. Keep on keeping on. Bye.